observe it. And so typically you take a sample, and from that sample, you calculate statistics. And so now we've had some opportunities to see some of those statistics. So things that we've been calculating, like X bar, the 5-number summary, right? Those types of things. Those are all example statistics. And there's also, graphical summaries, histograms, box plots, things like that. That all kind of falls in that category of general statistics that describe a sample. But ultimately, there's another step, because usually what we're interested in doing is we're typically interested in doing some sort of estimation about what's happening or what's going to happen. And that's because to estimate those parameters, what we're trying to do is we're trying to figure out what's going on at the population level. That's typically, or we're trying to predict things that are going to happen in the future that we can't really be that sure of. Statistics isn't really it's not really a science, and it's really not even a pure math. It's more of a philosophy. Sort of like an educated guessing game, but we try to use mathematical principles and foundations to make the most educated guesses that we can. That's the idea. So anyways, we're going to get into some of this stuff right here, making estimations. And if you remember, this is called the inferential step or inferential statistics. And the reason being because inference is kind of another name for educated guess. So we're going to actually get a chance to see how we can do some inferential statistics. And we're specifically going to be looking at like 2-variable analysis. So everything you did on your test last week, we were mostly just looking at like single variable analysis. Like you were just graphing or working with the prices of food, right? That was like a single variable. Or you're just looking at, like lengths of pregnancies. That's a single variable. So today, and it's chapter 12 in your book, but it's module 4 in this thing. It's kind of goofy, but that's what it deals with, 2-variable analysis. That's what we're going to work on. Okay? All right. So first we're going to look at comparing 2 quantitative variables, because, right, your data type matters. Quantitative variables are just a lot easier to work with mathematically, and so we're going to look at that first. So we're going to be looking at how to compare 2 quantitative variables. Typically, we know that you should always start with a graph, and so we're going to start with scatterplots. And so a scatterplot, right, is like typically what you have is in a data set, you might observe 2 things about a person. So, you'll have person 1, 2, 3, 4, up to your sample size. And then maybe you're going to observe some X variable and some Y variable about them, right? So for each person, you're going to observe 2 things about them, right? And so it could be, you could observe a lot of things about people. You could observe their age and their, how many miles are on their car or something, right? Those would be 2 quantitative variables. And so for everyone, you'd have, this person you'd observe their age and how many miles were on their car or something. And then what you could do, right, is you could just make a little XY axis, and then you could plot points, right, on a coordinate system. So, whatever they told you their age was, this might be their age, and whatever they told you the miles on their car was, it might be there, and then they get a point, right? X1, Y1. Yeah. And then you just do that, and you graph it. And I just made that one up. I don't really know that there's probably any relationship between people's ages and the number of miles in their cars. I don't know. But anyways, you graph it, and you're just looking for patterns. Okay? Is there some relationship between one numerical variable and the other numerical variable? That's all. Okay. And the reason we're going to be looking for patterns is because if there is a pattern between 2 quantitative variables, it's possible that you might actually be able to predict one based on the other, which is the goal. So the whole goal of this first part of this module or this chapter is we're going to be looking at, okay, well, how do we measure the relationship between 2 quantitative variables? And if there is a relationship, how can we use one to predict the other? So, all right. So I'll give you an example. This one, I need to get some updated data, but anyways, this is some older data, but one day I'll manage to update it. And this was just a couple randomly selected domestic cars. This data came from 2015. So what it shows is it just shows the weight of the vehicle, and it shows the average miles per gallon that they get. And you could imagine there's probably a relationship, and the relationship's probably what? Yeah, heavier vehicles probably have less fuel efficiency, probably, in general. And you could probably just observe that if you just look at the data set here, right? So you can pick out some of the lighter cars. The lightest one was a Ford Focus down there. It happens to have the highest fuel efficiency, and then the heavier ones are worse. So it's not that surprising. So anyways, when you get data like this, so now I've got two variables from each observation, then we can plot them on a scatter plot. Okay? And I'm assuming you guys are all capable of making a scatter plot, right? But just for fun, I'll show you how to make one. But so you got your x-axis, y-axis, and then we can label it here. So our miles per gallon look like they go roughly from like 15 to what, maybe no, this is our weight. I'm going to graph our weight on the x-axis. Reverse that. Our weights go from roughly what?
2960.
Yeah, 2960. So somewhere just a little under 3,000 up to about 4,800. Is there a 4,800?
It's
4,700. So I don't know. We'll just call it 5,000. That'll make it easier. Call this 5,000. So that would put 4,000 somewhere in here. And then our miles per gallon go somewhere from, I think, around 15 up to about 30. So if 30 is here, then the 15, 20, 25, something like that. So then you just plot points and see what it looks like. So for your first observation, they had a weight of 4,700. That was somewhere, maybe around there. And then their miles per gallon was 17, which is somewhere around here. And so it doesn't have to be perfect, but that point would probably be about right there. So this would be 47, 24, 17. Yeah? Okay. And then you just do that for every single vehicle, and then in reality, you probably just let a computer do it because it's a lot faster and probably prettier. But it's not that hard here. There's not that much data. So the next car, 4,000 pounds and 18 miles per gallon? That's somewhere around there. Then you got a 3,000-pound car, just a little over 3,000. It gets 22 miles per gallon. Then a 3,500 car gets about 19 miles per gallon. 4,000-pound car, just a little over, gets 19 miles per gallon. Then you got another just under 4,000, about 19 miles per gallon. Where are we at? 3,200. The Dart's 3,200 pounds. It gets 24 miles per gallon. So, somewhere around there. And then the Focus is just under 3,000. It gets 26. That's somewhere around there. Then you got the Mustang 3,500 at 19 miles per gallon. So roughly right around this person there. And then what else? The 3,800 at 18. So 3,800, maybe 18, somewhere in this range or something. Yeah? And you're just looking for that pattern. You don't even really need the label here. I was just kind of showing you. But probably the labels make them harder to read. And so, obviously you can see a relationship here, right? What's happening? As one goes up, the other goes down, And the pattern is actually, it's not perfectly linear, but it's pretty linear, all right? And that's why I had you take a quiz reviewing linear equations, because what we're looking at is, we're going to be looking at a process called linear regression, and what it does is, linear regression takes plots like this and tries to determine what line best describes that relationship. Is there a line that you could fit to that data that would reasonably describe the relationship between the weight of these vehicles and their fuel efficiency? Yeah, and you can imagine, it's not that hard to imagine what it would be, right? You can imagine it looks something like, that, right? There's some line, and you could tweak that a little bit or whatever, move it around, but it's something like that. There is some linear relationship that would describe that pattern. True? Okay, so that's the idea. So you can make your scatter plots. Now, the thing about it, though, is, we're looking for that linear correlation. Well, actually, I guess I'll define it first. But the linear correlation basically says that linear correlation exists, say, between two quantitative variables. If as one variable changes, the other also changes, also changes in a linear pattern. And so it could go, one could go up as the other goes up, one could go down as one goes up, right? They don't actually have to go, and it doesn't have to be on the same scale. It's just that as one variable changes, you recognize that the other variable is also changing, and when you plot them, they have that linear pattern to them. So that's called linear correlation. It just means there's a pattern, basically. Correlation is almost synonymous with the word pattern. Okay, it gets complicated when you start looking at correlation of like non-quantitative variables or like multiple quantitative variables, because then it's like, what does a pattern look like in 5 dimensions or something? It doesn't make sense. But in 2 dimensions, it's basically correlation is the same thing as pattern. Okay. All right. Now, you can recognize, so far so good? Everybody good? All right. So you can recognize linear correlation pretty easily from a graph. That's one of the reasons that graphs are so important. That's why you should always start with a graph. Because our eyes are good. Like, our eyes are pretty good at recognizing patterns because that's just something humans do. So, but from a quantitative analysis standpoint, we like to have some sort of measurement that helps us understand how strong the relationship is. Because there's a difference between, like, this data set is nice and linear, and you don't have to draw this, but you could come up with some other data set that also has a linear relationship, but maybe it's not as like straightforward, right? So like if you look at that scatter plot in the bottom right, there's still a relationship, but is it nearly as strong or predictable as this one? Not really. Okay? And so we want to have a way to quantify, are we dealing with the big graph or are we dealing with a situation like the small graph? Okay? And so statisticians, and I say we, I didn't have anything to do with this happened like 100 years ago, came up with the correlation coefficient. Okay? All right. There is a very complicated formula for the correlation coefficient, and you don't need to know it because it's a waste of time. It's kind of like the standard deviation formula. I taught it to you, but then you don't really need to know it. You can just get that out of your calculator. But I'm going to tell you what it does. Okay? So what the correlation coefficient measures, so the correlation coefficient, it measures the strength and direction of linear correlation between 2 variables, or more, but we'll do 2 for now. Okay. And it's always, it's like a little n always denotes sample size, little r always denotes correlation coefficient. Little s always denotes sample standard deviation. It's one of those common ones that doesn't vary from book to book. It always means the same thing. And the way the correlation coefficient works is there's a couple properties of the correlation coefficient. The first is that the correlation coefficient, the formula is set up so that the correlation coefficient is always between -1 and 1. Always. So no matter what data set you throw into the formula, it's always going to return a value somewhere between -1 and 1. Right? Then, the way it works is, if you have, so I'll draw you some pictures to explain that. I don't know why I drew an arrow there. It doesn't really need to be there. So if you had a data set that returned a correlation coefficient of r equals 1, what that would tell you is that would be what we would call perfect positive correlation. So, like if you took a linear equation, like maybe one of the ones I put on the quiz, like if you took a linear equation and you took like 6 points off of that line, and then you calculated the correlation coefficient of 6 points that fall in a perfect line, the formula would turn back a correlation coefficient and it would say your correlation coefficient is 1. Your data is perfectly linear correlated with a positive slope, right? And we talk, so slope is like the line, how steep the line is and which direction. If you have a positive slope, that means as this variable is going up, that one's also going up. Excuse me. So then you imagine you could also have what? Perfect negative correlation. That's where the -1 would be. So if the correlation coefficient was -1, then that's telling you that you're dealing with data that has perfect negative correlation. Okay. So it's possible to have perfect positive correlation. It's possible to have perfect negative correlation. And it's possible that two variables could have what? Absolutely no correlation. Like, for example, like the age and the number of miles on your vehicle, that's probably very loosely related, if related at all. Okay. And so in the middle, a correlation coefficient of, say, r equals 0, that would be two variables that have like absolutely no linear relationship. Okay. Okay. So far, does that make sense? So it's a number. Now, the thing is you could calculate it by hand. I don't think that's necessary. In the modules, what you need, just what I put up there in the modules, blah, blah, blah. I need to reorder these and send the old ones down to the bottom. I made a little regression calculator. You can do regression calculations in Excel. You can do them. There's all sorts of like statistical software programs you can get that do linear regression analysis. Your TI-30s may do it, but I don't. I think they do it, but it's not as intuitive. So I just made a little Excel file that you could download and play around with. So I'll pull that up. And so you can just see how a typical software program would typically handle data and display the output. Okay, so like here, I downloaded it with the car data preloaded into it. So what you could do is you could change your X and Y values and see kind of what happens. But typically the way a software program will handle it is it'll have you put all of your one variable in one column, it'll have you put all of your other variable in the other column, and then sometimes it'll display graphs. Although my graph's acting really goofy. For some reason, my graph, excuse me, always wants to start with the origin at the center of the XY axis rather than scaling it. If anybody in here knows anything about Excel and knows how to get rid of that, you should let me know, because I can't figure out how to undo it. But anyways, most software programs will plot it better than me, but that's just my best attempt at it. And then they'll usually give some summary output. So like here, the first thing I provided for you was the correlation coefficient between those two variables. So like you can see for the data that we looked at, we knew that it had a negative correlation. And it's pretty strong. The correlation coefficient for that data set's like negative 0.84. That's pretty close to negative 1. And so it's telling you that there's a pretty strong negative linear relationship between weight and fuel efficiency. And you could mess with it a little bit, like let's say if we really mess with the pattern, so let's say we took the really heavy car and made it really fuel efficient, right? That really screws with your correlation. So did you notice what happened to your correlation? It went to like 0, and that's because what did we do? We threw this like outlier in there, and now the correlation, it doesn't know what to do with that information, because it's like, okay, well, what's going on here? Because is there actually, if I get more data, am I actually going to see like a pattern that goes like this? Or is it that's actually a pattern and you got an outlier there? You know, if it wasn't as extreme, so that's a pretty extreme case because that's a pretty big outlier. Let's say maybe it was more like 23 miles per gallon or something. You know, there's still some correlation there, but it's just not as strong, right? And you can see it in the graph, because just by looking at it with your eyes, you can see, oh, that's not a strong correlation. Okay? So, anyways, we're going to mess around more with this in the meantime. I don't remember what that number was supposed to be. What was that number supposed to be? 17. I'll go fix that, because we're going to come back to that. I also gave you some other information there, and we're going to talk about that in a second. But in the PowerPoint, there's this little fun game. It's not that fun, but fun's a subjective word. We'll just look at it real quick. I think it works. But it's just like this stupid little 45-year-old from the birth of the internet game. I don't know. but it just like allows you to guess correlation coefficients to just kind of get familiar with what type of data has what type of correlation coefficient, because our eyes are pretty good at recognizing patterns. But the nice thing is it gives you 4 graphs and then lets you pick from 4 different correlation coefficients to help you start sorting out kind of what they mean. So like, for example, here, like this one in the top left has to be what? It's got to be negative, and then you can look at the 2 graphs with negative correlation, and then so this one must be which one? Yeah, the top left has to be negative 0.9 because it's negative and it's much stronger than the one below it. So the one below it would be negative 0.76. And similarly here, this is positive and it has to be the 0.94 because the one below it's not as strong. And so you start to get an idea of what the correlation coefficients look like when you translate them into scatter plots. So this is a data set with 0.76 correlation, negative. This is what a data set with like 0.94 correlation would look like. So we could check and see. And it's very sophisticated graphics. So we can, yeah, the little green smiley faces. And then some of them aren't as straightforward, but they're not too hard to parse out. Like this one's got to be what? Negative. That's got to be negative, and it's got to be which one? Yeah, it's got to be the negative 0.84 because this one's also negative. It's just not as strong, right? And same with positive, right? So this one's got to be positive. This one's got to be positive. One of those looks a little stronger to me. Which one do you think it is?
The top one.
I think the top one's a little stronger. Okay. This one's probably a little weaker, right? I just kind of like squint. You just like blur your eyes a little bit, and then you see which one turns into a line faster. That's the one with the better correlation coefficient. But that's my strategy. Yeah, it's statistics, guys. Okay, it's just yeah, it's just. But anyways, you get the idea, right? Some of these are pretty close. Like, which one of this is 0.7 and which one of these is 0.69? I don't really know, but good luck. I'm gonna guess.
The bottom right one, yeah.
You think this one's the weaker one?
Yeah, outlier. Yeah.
Yeah, it's got the outlier. Okay, I'll go with your guess. And then what about these two? These ones are relatively close, but this one's a little weaker, I think, right?
Yeah,
this one's a little stronger. So that'd have to be the 0.85, yeah, and that'd have to be the 0.71. And then the other two kind of, oh, there you go. Good job. All right. There you go. Okay. You get the idea. All right. Now, you want to play again? We could play all day, right? Yeah, we could just play this game all day. It's really that fun. But you can play it on your own. You can get this link in your slides and use your own web browser at home. And you could also play if you want. Or you could pull it out at a party and play it with your friends. You could turn it into a drinking game, maybe. I don't know. So, anyways, yes. I don't know. I mean, all the statisticians I knew drink pretty heavily, honestly. So it's a mathematician thing too. Anyways, what are we talking about? The point is that it's a number. It exists. There's a formula for it. It's not that important because a software program is going to spit it out for you. You just need to know how to interpret it. So if that's negative 0.84, you can be pretty confident this is a pretty strong relationship. If that number was like negative 0.07, you could say, okay, this is not a linear relationship. There's no point in fitting a line to this data. So it's like a check. It says, is this a good data set? Is this data set a good candidate for fitting a linear equation to it? That's the idea. So this data set is. Okay. So like here, well, I gave it away because I already gave you the correlation. But if you look back at our plot here, right, you probably would have guessed, you might have guessed it was a little higher, but that's just because my drawing is not very good. So you might have guessed maybe that was maybe negative 0.9 or somewhere in the area. But we can see from our actual data set, oh, don't worry about this. I'm not going to worry about that. From the actual data set, it looks like it's, what did we say it was? It was like negative 0.84. Okay. So I'm just going to write it down real quick so I have it for later. Do some toggling here. Oops. What the heck, man? Go to pen. What was it, 8.4 or something? 8416. Yeah, it came from the Excel file. So, okay. So you can download that Excel file and kind of play around with it a little bit if you want. If you totally mess it up, that's the reason originally I was going to do it in like a Google Sheet or something. Then I realized if you guys got in there and started blowing things up, it would mess everybody else up. So if you mess it up, just delete it and you can re-download it. But anyways, okay. Now, one important thing to talk about here is, remember, so the correlation coefficient is talking to you about correlation, but it's not necessarily telling you anything about causation. And this is something we talked a little bit about at the beginning of the course when we talked about observational experiments versus observational studies versus experiments, right? So correlation, I told you, is just another name for pattern between the two. Okay, and whereas causation is one changing causes the other to respond. So, and those are two very different things, right? Because you can have a pattern between two variables, but they don't have anything in common. Okay. So, some of you guys may take it like psychology. I think they talk about this in psych here. Like I think if you take like psychology 101, do we have psych 100 or is it 101? I don't remember. 101, yeah. It's they talk probably about correlation causation. There's a website. I don't know. Someone over there shows it too. There's a website called Spurious Correlations. Did you guys see that? Did anybody ever see that? Spurious Correlations. So what this guy does is he just finds data sets that have that just have ridiculous correlations. So like if you look at, for example, the number of people who drowned by falling in a pool in a year and the number of films that Nicolas Cage appeared in that year, there's a really strong correlation between drownings and Nicolas Cage appearances.
So it's not a causation.
Right? Yeah, but obviously Nicolas Cage is not causing people to drown, or at least we hope not, right? And so, but you can just find, it's kind of, what is it? There you go. Per capita cheese consumption is highly correlated with people dying by becoming tangled in their bed sheets, which is a very strange, it's kind of morbid. There's a lot of morbid ones on here, but you can see, like, you can see the pattern, right? And there's just really high correlation. There you go. There's an interesting one. The divorce rate in Maine is highly correlated with per capita consumption of margarine.
9%.
Yeah.
That's crazy.
Yeah, the correlation coefficient is absurd.
Where did you find this stuff?
I don't know, actually. I have a suspicion that this guy is just data mining, like Bureau of Labor, like he's just data mining some large databases, and he's just having a script just run like millions of correlations until it flags things, and then the most absurd ones he just picks and graphs. That's my guess, if I had to guess. I don't actually know, though. But anyways, obviously there is no causal link between margarine consumption and divorce rates, right? Why do you think there's a pattern between margarine consumption and divorce rates?
Who's trying to eat healthier?
Well, I don't know. You can see that there's a trend, right? What's the trend over time?
It's going down.
They're both going down, and so why do you? But they're both. Sorry, go ahead.
I would say the less margarine you eat, the less likely you are to get.
Well, that would be causal, though. That would be suggesting that there's a causal link, but I don't think there is. What do you think is really explaining this relationship? Why do you think there's such a strong relationship between margarine consumption and divorce rates?
The population keeps changing.
The population's changing over time, and what's happening within the population? Like, just in general, what's happening to people's margarine consumption?
It's going down because they're not eating.
Yeah, margarine consumption is going down because people found out that, like, mutant fats that you make in a lab actually aren't that healthy for you, right? And so margarine consumption just over the last decade or two is just going down, right? Well, what's also true about divorce rates?
People aren't eating.
Yeah, divorce rates have historically been trending downwards since, like, the 70s or 80s. They kind of peaked, I think, in the, I don't remember, 80s or something like that, right? Because they're just going down, because people aren't getting married as young, people aren't getting married as often. People who get married tend to stay married longer. Okay, so divorce rates are have been going down over time. Margarine consumption's been going down over time, and so that's why you see the relationship. They have nothing to do with each other. Okay, so that's the point. So if you ever want to look at some weird ones, Yeah, so this comes from Department of Ag and the CDC. So my guess is probably what he did is he just compiled a whole bunch of governmental data sources over time and just ran a ton of regressions to see what happened and just picked out some of the weirdest ones. That's my guess. Anywho, who has data on Nicolas Cage appearances? I don't know where he got that data, but yeah, I don't know. Yeah, the government has a big interest in Nicolas Cage. I don't know. Anyways, okay. So here's another example that I use sometimes thinking about correlation versus causation. Sometimes it's not that clear. Like obviously, margarine and divorce rates don't have anything to do with each other. Probably, I would guess. It'd be really weird if they did. But like, here's an example. It says page 189, but that's not true. This came out of an old book. But anyways, this is looking at bone mineral density versus cola consumption. Right? Now, what's going on here? There's obviously a pattern, right? What's the pattern?
Coffee drink
Yeah.
or soda drink.
As women who were recorded, the women who consumed more soda per week, they recorded lower bone mineral density numbers. Okay? And you could probably guess here. What do you think the correlation coefficient here is, maybe? What do you guess? It's got to be what?
Negative
It's got to be negative.
Like negative 0.6.
Yeah, maybe somewhere in there. I don't know, negative 0.6. Somewhere between maybe negative 0.6, negative point. I'm just going to say negative 0.6. That's close enough. It's good enough. Okay. So, anyways, something like that. So it's not trivial. It's definitely there. The pattern's there. Now the question is, do you think this is a causal relationship or do you think it's a correlation? See, that's the thing. It's not always so clear because it could be. So I'll just say, could be. So it could be. So some people say it could be causation. Why?
It's like drinking a sugary drink and it might deteriorate your bones.
Or you probably just getting less exercise.
Well, so is that the soda causing that or not? Now, it could be that there could be something about soda. So there could be something about soda that actually lowers bone mineral density, right? So I don't know what's in it that could.
CO2 is what I heard.
Yeah, it could be. Maybe there's something about CO2. Okay, maybe there's something about sugar or something. I don't know, right? It could be causation. Maybe. Now, it's also possible that it could be correlation, right? Because it could be correlation because why?
The people that drink more just aren't as active, and because of that.
Yeah, so you have to think about soda drinkers may be more likely, and we're talking, this is on average, right? May be more likely on average to what?
Have a bad diet.
Yeah, it may be that maybe soda drinkers, people who drink more soda, may just in general just have a poor diet. I don't know. It's possible. Okay. It may be that people who drink a lot of soda in general may what?
Not exercise.
Yeah, exercise less.
Drink less water.
Right? Especially like load-bearing exercises or increase bone mineral density or retain bone mineral density throughout your life. What were you gonna say? What was the last thing?
I said just drink less water.
Yeah, and I don't know if water's correlated with bone mineral density, but I would just lump that into poor diet. It could be that they have poor diet. It could be that they exercise less in general. I don't know, right? But there's a lot of factors here that go into what may be describing this relationship. And so when you see a correlation, it's not necessarily declaring a causation. So this is an example where like an observational study might find this trend, and they say, hey, look, we found this interesting correlation between bone mineral density and cola consumption, but you can't really necessarily demonize soda as the cause of lower bone or mineral density until you had some sort of experiment to actually prove that, where you had some controls. Does that make sense?
What
So-
would you say here? Would you say it's both? If like you were asking if it's causation or correlation, would you just say, well, it's both?
I mean,
You don't really.
you don't really know.
Right.
I mean, what you would do, I mean, if this came from some observational data, you would say, this would be an example where you would say something like further study needed, like for further experiments,
Right.
more well-designed experiments would be necessary to tease out that correlation. Yeah, there was another one. Actually, I should have brought the article. I didn't have you guys read this article, but there was one in Science not too long ago where it was just like this. They actually found they found a high correlation between certain gut bacteria and like depression levels or self-reported depression levels among people, where there's a really high correlation between the presence of certain gut bacteria and people's likelihood to report depression symptoms. But it's just an observational experiment, so they do a good job in the article of saying, we have observed this pattern, but really what we need to do is we need to do some observational studies where we actually like intentionally introduce this gut bacteria or withhold it from people to see if it affects their depression symptoms and things. Okay, so yeah. It seems to. Yeah.
Even if, like, your teeth are bad,
Well, the teeth one, yeah, the teeth is an interesting example.
it, like, I don't know, it messes with your mental health.
Yeah, it is really interesting because gum disease is highly correlated with like heart disease. But the question is if you were a person that had gum disease and then all you did was change how you took care of your teeth, would it change your risk of heart disease? Like you didn't change anything else. Would it?
No.
That's the thing, because you have to think about, I mean, what makes people more susceptible to gum disease? Well, it'd be like poor dental hygiene, but poor dental hygiene could be associated with a lot of other things that could also make you more susceptible to heart disease, right? Because people with poor dental hygiene may be more likely to have a poor diet, or they may be more likely to be more stressed, or they may be more likely to be depressed, or something like that. Okay, and those things could bear on your risk. So that's the thing. It's really just, who knows, right? I mean, humans are just weird. Like, we're just very complicated creatures. It seems like there's something there. But anyways, you get the point. Okay. Now, whether it's correlation or causation, it doesn't actually matter if you're trying to do prediction. Because if you told me how many sodas per week a woman consumed, could you use this graph to reasonably predict their bone density?
Sure.
You could, right? Like if you told me, say that if you come to me and you say, I have a woman who drinks, say, 5 sodas per week. Could you reasonably predict what her bone mineral density would be?
Between 8 and 7.
Yeah, you can see there's a pretty decent pattern here. My line's not perfect, but it'd be somewhere in that area, right? So you could actually make a prediction, and you could actually say, I would predict that person's bone mineral density probably somewhere around 0.87 or something like that. And on average, you'd actually probably be right. It's not going to be true for any individual woman, probably, because you can see there's variation at every level. But on average, and on average is really what people care about in a lot of situations. Like, if you're talking about like best practices or recommendations for like the FDA or for doctors or some medical association, or if you're talking about an insurance company, those people aren't necessarily, it's not that they don't care about the individual, but what they're most interested in is what's best on average. What's the recommendation, or what's going to happen in the long run over a lot of people. And so that's actually probably a pretty good guess. If you gave me 100 women that drank 5 sodas a week and averaged out their bone mineral density, it'd probably be pretty darn close to that number. And so whether it's correlation or causation doesn't actually matter if your goal is prediction. That's the point. Yeah? So it's like, I could actually really, if you told me how much margarine people were consuming in a certain year, I could actually pretty accurately guess what the divorce rate in Maine was that year, just using the correlation that's there. I could make a pretty darn good guess, and I'd be probably almost spot on, even though there's no causal relationship there. I could still use that relationship for prediction pretty accurately. That's the point. Okay. So here's the idea. So then, in general, the goal here, our goal is to use one variable to predict the other. That's our goal. Okay? And you could imagine this is a goal in a lot of scenarios. Like, why would you want to predict, margin and divorce rates doesn't make sense, but like, why would you want to, could you think of situations where you would want to predict one variable based on another?
Insurance.
Insurance is a great example. Like, I want to predict how much money, you want to predict, I come to you and I say I want insurance. I want you to insure my car, right? Well, then you need to reasonably be able to predict how much money am I going to cost you in the next 6 months? You know, what's the likelihood that I'm going to drive my car off a bridge? What's the likelihood that I'm going to back into someone? You know, like you need to be able to reasonably predict, but you can't actually know those things. So what do you have to rely on instead?
Driving insurance.
You have to rely on all sorts of other information about me, like my driving history. Do I have kids? Do I have a job? Do I have, whatever, things like that. And you have to rely on certain variables in order to predict others. So that's where stuff like this really comes in handy. It's also for like medical testing. You know, if I'm trying to diagnose someone with a problem, I can't actually necessarily observe directly, at least not cheaply, whether or not they have a certain condition, but I could run a lot of tests that are highly correlated with that condition to try to narrow it down. Okay, that's the idea. Okay, anywho. Now, what has to happen, though, is once you have data, though, you have to actually pick what line is the best line, right? So how do I decide what line is best? So you don't have to write this down. Now, this is the process. It's called least squares regression. And I'm going to draw you a picture to show you how it works, but you don't need to know this. Or you need to know how it works, but you don't need to draw this picture, unless you just want to. Okay, so let's say I have some data. Okay, and I'll just keep it small for this example. Okay, so let's say I have maybe a couple data points. All right, and I'm trying to decide what line, what is the line of best fit is what it's called. Sometimes it's like, what line is the best line to describe that relationship? Did I draw the best line? Probably not. Because if you move it, you can move it up or down, and you could like tinker with the slope. The question is, well, so how do you decide what line is the best line? Right? I don't know. Okay. Now, what you do, the way we ultimately typically do it in statistics, then is we say, all right, so think about the goal. The goal is to make predictions. So I have some x variable here, and I have some y variable here. Right? So now here's a person right here. Okay. And so here's their x, say that's person 1, right? That's their x variable. Now, what happens is if you look at the line, where does the line say they should be? The line would predict them to be right there. Okay? So, but in reality, what happened?
They were under it.
They were under it. Okay? So here's their actual value, but this is the y value that my line would have predicted them by. So in statistics, when a number's been predicted, we use a little hat. Now that's not that important, but the hat means it's been predicted. That's how you know whether or not it's a value that was actually observed or a value that was predicted. So what happens here is the line made a mistake, right? And so it made an error. So we'll call it E for error, So this is called an error, or sometimes it's called a residual. It's like what's left over, what's residual when you make your prediction. Okay. So, but what happens is every single point. So you could think of this. This is like error 1. This is error 2. Right. This is error 3. Error 4. Error 5. And error 6. Right. So for all 6 of those points, your line made a little bit of error, and some people would be underestimated, some people would be overestimated, right? Now, what happens if I move my line up?
Everybody's going to be underestimated.
So if I move my line up a little, what happens to all those errors on top of the line? They get smaller, but what happens to all the errors? They go up, right? So the thing is like as you tinker with that line and you change the slope and you move it up and down, you're constantly making some errors bigger and some errors smaller. Now, of course, the problem here is like the problem with standard deviation is that you kind of want to like average them out, but some of them are negative and some are positive. So how do we deal with them in the standard deviation? How do we make them all? We squared them all. So what we do is we go through and we say, well, then we'll look at the sum of all of the errors squared. Okay. So this value right here, this is called the sum. Again, you don't really need to know this. I'm just telling you how it works. But this is called the sum of squared errors. So you take all those errors and then you square them and you add them all up and then you tinker with that line until what we do is we minimize. So we minimize this sum. So, and you can actually do that mathematically. You can actually find the values of the slope and the intercept that will minimize that sum. And that's why the process of fitting this line to the data, it's called least squares regression, because it's literally the line that produces the least sum of squares of errors. That's the idea. So that's how, now, there's formulas for this, but again, typically, you just let a computer's just going to spit that data out for you. Okay? And that was some, if you notice on my Excel spreadsheet, that was some other information that was provided on that spreadsheet. So you see, under the correlation coefficient, this is something called the coefficient determination. It's not that important. You don't really worry about it. But then I also gave you the intercept and the slope. And so what these are is, this is telling you what the y-intercept of that line should be, and this is telling you what the slope of that line should be. And these are found using least squares regression. And then I also showed you the line, what the actual line would look like. That would be the equational line. And so the line that you end up fitting is, this is called the line of best fit. And typically, it's like, in algebra, it's always like mx plus b. For some reason, in statistics, we usually use it's normally in this form. We always put the intercept first. In statistics, we usually put the intercept first, and then we put the variable term second. And whereas in algebra, you're used to seeing it the other way. It's usually like slope intercept. But that's because you can do regression for like multivariable. So you can start tacking in. You can actually start tacking on more variables at the end, like another variable or like an x squared variable or something like that. And so we build it that way. But anyways, that's the idea. Okay. So then what you get is you get a line, and that line is what you can use to help you make the predictions. And this is about, we don't really have time to do this. We'll pick up here tomorrow. But the idea is then now I have a line so that if you tell me the x value, so if you give me a weight of a vehicle in that class, then I can just plug it into my equation, and my equation will just spit out a prediction for that vehicle's fuel economy. And on average, it's probably very accurate. And that's the idea. So tomorrow we'll actually use this line, and we'll look at another example. I'll show you how to use the line, and we'll talk a little about interpreting it. But that's where we'll pick up tomorrow. Okay? Don't forget to take your quiz tonight if you haven't.